Greetings. I'm introducing our recent work here about learning nearly unsupervised hashcode representation for relation extraction or any other NLP task. In our previous work, we proposed to map any NLP structure to a large binary hash code using the concept of kernelized locality sensitive hashing. And then these hash codes can be used as feature vectors for classifiers like random forest, and it shows state of the art performance for biomedical relation extraction tasks. And the locality sensitive hash codes can be built using a randomized algorithm where each hash function is constructed using a few data points which are a subset of the whole training set. And this way, since each of the hash function is constructed from different subsets, we have this principle of randomization applied here for learning more robust representations. And so basically you have some data points and you assign them some labels, so-called artificial labels, and then those labels can be used to construct a hash function. And you could even optimize these labels as we would see later. To optimize these hash codes, in the previous work, we proposed to maximize mutual information between hash codes and the class labels of the NLP structures. And to compute mutual information efficiently for these high dimensional hash codes, we proposed an approximation which is also present in the previous work. And now we try to improve our work. Specifically, the limitation of the previous work was that we were only optimizing global parameters of the hash function, the parameters which are common, for instance, kernel parameters or the set of sentences which were being used to construct this hash function. Now we want to use all of the information, all the sentences in the data set to construct hash function rather than being restricted to some subset. And rather than just optimizing kernel parameters, we do more fine-grained optimization. So how do we do that? We considered specifically near unsupervised setting for the learning, where this blue data distribution represents label examples, say training set, and this red data distribution represents, say, test data in transductive settings or just unlabeled data in inductive settings, some unlabeled data used to improve, build semi-supervised algorithms. And say for instance here you are having just 4 data points to construct a hash function. In practice you could say have 100 or 1000, and we will try to see what kind of hash function could be optimal that factorizes this, for example, and so the whole data distribution. So like this is one example where I have assigned one label to these 2 examples and another label to these 2, and correspondingly when I fit some classifier or any model to these 4 data points, or even like 1000 of such data points, then I would learn some kind of boundary which could be also highly nonlinear. But then there are other choices, and the question is which choice is better, and you could even have many more choices as you see here. And what we say is intuitively we want to learn a hash function which is generalizing across training and test data, especially when you only have the information of which data point is coming from training and test. Then you could also add additional information like the class labels when optimizing this function. Further, we say that we want to do some kind of regularization of these hash functions. How do we analyze that? The idea is that hash function can be used also for clustering data and not just for representation or nearest neighbor search. For instance, all of these black lines, each of these are some hash functions, and the intersection or like the joint use of this hash function is giving us clusters. So these shaded regions are clusters. Now the question is which cluster is better? On the right hand side you have a cluster which have both training and test examples, and that's what we desired. So we can define this criteria to just see the quality of the representations, that it should have clusters containing both training and test data, which is also a very common criteria considered in semi-supervised learning models in one form or another. And further, the question is how do we sample these data points which are used to construct a hash function, this subset of data points. One option is that you could do global sampling. Another option is that you could sample it locally from a cluster, and that's what we propose. Further, you could even decide which cluster to sample from. For instance, we propose to choose a cluster which has both training and test examples. To ensure non-redundancy of the hash function, we say we intuitively want to have a hash function which cuts through other hash functions. We are looking forward to seeing you at the poster. Thank you. Bye.